So section 11.6 is all about surfaces in space, and we start off with cylindrical surfaces. Okay, and typically when we think cylinder, this is what we think. We think of a kind of, cylinder, right? That's what we think of. We think of this. But this is actually a very specific kind of cylinder. This is a right circular cylinder. Cylinders actually are a much broader family of surfaces. So let me give you the definition and then I'll give you a few examples. So the definition for cylinder. Okay, here we go. Let C be a curve in a plane. And L be a line not parallel to that plane. Okay. The set of all lines parallel to L and intersecting curve C is a cylinder. Okay. C is what's called the generating curve or the directrix. So C is the generating curve. C is called the generating curve. Okay, just meaning that that's what it is. So here's how I kind of think of a cylinder. If you've ever seen a space movie where there's some ship in space and the ship takes off, but it kind of leaves a trace of itself behind, like it's being extended, that's always how I've imagined a cylinder to behave. You start with the curve itself, or in my analogy, the ship, and then it extends along some linear direction. That is creating a cylinder. Okay, so a cylinder does not have to be circular, does not have to be closed. Any surface, any curve can generate a cylinder. So for example, suppose XYZ, suppose I have a parabola in the YZ plane here. So suppose it looks like this. So this is just a parabola in the YZ plane. I can extend lines, all parallel lines, through this parabola. So I'm going to choose to do that right through, lines that are parallel to the x-axis, just for prettiness sake here, but it could be at any angle. So I'm going to go ahead and extend this through here. And again, I am attempting to keep this parallel, right? Okay. So what's going on here is we have got kind of a repeat of this parabola all along these lines. Oh, that was terrible. I'm going to undo that one. In this case, it kind of looks like a folded taco shell, right? So we have a parallel line that cuts through here, 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 hits the same point on all parabolas throughout. This one coming through here again is hitting the same points all throughout. Down here at the bottom, hitting the same points all throughout, at least it's supposed to be if I could draw properly. There we go. Okay, so draw that one back in. There we go. All right, so what we're doing is we are just kind of extending this curve along some line. So we're making it we're turning a single curve into a surface simply by extending it. So it's going to be uniform all the way through. So this is a cylinder. Okay. And since this cylinder is running parallel to the x-axis, the equation of this cylinder will not have an x in it because x doesn't affect the value. The parabola is going to be the same for every single x value. So the equation for this particular cylinder is going to be z equal to y minus 2 maybe squared, because this looks like the parabola maybe was shifted to the right 2 spaces along the y-axis. So we have z equal to y minus 2 quantity squared. So there's a parabola. There is no x here, so we know that the cylinder is running parallel to the x-axis. Okay, so now let's go ahead and sketch one. We'll do an example where we get to sketch one. Sketch the cylinder given by, let's see, z equal to sine of x for x between 0 and 2 pi. All right, so the first thing we want to do is we want to sketch the trace in the xz plane. Okay, so this is a little bit difficult for us to kind of get our heads around sometimes, so we want to be cautious of that. But this is just z equal to sine x. And if we have y equal to sine x in the xy plane, okay, we know that that's going to start at 0. It's going to come up, come down, hit at pi, come down, and come back up and back at 2 pi. All right, so it's going to do exactly the same thing on the xz axis. So we're going to begin at 0. We're going to come up 1, up to 1, and we're going to end up going down to 1 as well. So we're going to come up to 1 and hit here. So this would be at pi. And then it's going to dip down below and come back up and hit at 2 pi. Okay, so there it is, and that is the trace in the xz plane. Then it's a cylinder, so it's going to be extended parallel to the y-axis. So I'm going to draw some horizontal lines parallel to the y-axis here through kind of the special points. Okay, so this is just going to repeat over and over and over again. So we're going to have it come from here, up to here, down, hit here, come down, hit here, and then come back up. So you can see that I'm just repeating this curve over and over and over again. Oh, and I did stop at 2 pi and 0 because those were the boundaries we were given for our x value. Okay, so this is just going to keep going over and over. It's going to repeat over and over. Okay, and so there you can see our surface. So I will do my very best to shade this in a way that might make some sense. So this is the kind of outside here, and so that would appear to be here as well. And then this, the fold over part of it, I'm going to kind of make that blue, and so we can see kind of this coming down to here. Okay, so like if you had a curvy piece of paper sitting there, just kind of folding down, coming up, and folding back down. All right. Now the arrows here are indicating that it does keep going. Okay, so it's very important to make sure you include those if you have to do any sketching. Okay, so now we're going to move on and talk about quadric surfaces. Quadric surfaces. Now I'm going to do my best to draw these for you, but they are not going to look great on here. I'm no artist, and it's not easy to draw these things in 2 dimensions anyway. But I'll go ahead and give them each to you. So quadric surfaces are going to have a general form. So the general form, is it general or standard? One moment, technical difficulties. So it's general form. General form, where it's going to have basically every degree 2 possible combination of x, y, and z, the linear terms x, y, and z, and then a constant term equal to 0. So we have got a x squared plus b y squared plus c z squared plus d xy, there we go, plus e xz plus f yz plus g x plus h y plus I z plus j equal to 0. Okay, so all of these quadric surfaces are going to fit into this mold somehow. It just depends on which of the coefficients are 0 and which ones aren't. All right, so the first one, there are 6 of them in total. So let me write that down. There are 6 types. The first one is the ellipsoid. Okay, so this one looks kind of like a football or any kind of elongated sphere would fit into that. A sphere is technically an ellipsoid. Elongated spheres would be ellipsoids. They're going to be given by the formula x squared over a squared plus y squared over b squared plus z squared over c squared equal to 1. All right, and just like an ellipse in 2 dimensions, the axes along the axes of the ellipses along the different axes, the coordinate axes, those are going to be given by A, B, and C here. Okay, so let me just put a nice box around that, and I'll do my very best to draw you a picture. So just bear with me here. Okay, so in the x direction, we're going to come out A. So that's going to be our our ellipse there. So that's the trace in the xy plane. Then we have B. So I don't know how big B will be, but I'll put it here, negative B. So that will come out this way. And then finally C in the z direction. So I'll just put that right here. That's going to come out this way. Okay, so we have this lovely kind of ball thing going on here. So please, again, forgive my terrible drawing skills, but this is what we've got going on here. Okay, so an ellipse. So again, if I were to kind of maybe think about it this way, you know, kind of like that, maybe an egg, general egg shape kind of thing, more uniform than an actual egg. I am not going to spend all day. We could be here for hours with me trying to draw these things prettily, so I'm not going to do that. Number 2, moving right along. If you want to see nice pictures of these, you can find this in your book. So let me make a little note here for myself, for y'all. See pages 800 and 801. They have great drawings of these along with all of the details for it. It tells you how they fit onto the plane and everything, so you can see those. Okay. Number 2. The second one is the hyperboloid of one sheet. Okay. So it is going to look like this. Kind of an hourglass shape to it. And it's one sheet because it's connected. Okay. All right, so it looks kind of like that. And again, it is called one sheet because both of the ends are connected. It could be literally cut out of a piece of paper, of one sheet of paper, and formed. So this is the hyperboloid of one sheet, and the general formula here is x squared over a squared plus y squared over b squared minus z squared over c squared equal to 1. Okay? Okay, and we're going to talk more about these in just a moment. I'm just trying to get them down here on into the notes for you right now. Number 3 is the hyperboloid of two sheets. Okay? So this one cannot be drawn or could not be recreated with one sheet of paper. We would have to have 2 sheets of paper. It's going to kind of come up here like this, and then down here like this. Okay, so it's going to have 2 parts of it. It's not conical. It is more, well, hyperbolic. It's hyperbolic. So if you took the trace here in any of, like, for example, in the way I have it drawn right here, if you took the trace in the xz plane, you would have a hyperboloid. Okay, so the formula here is z squared over c squared minus x squared over a squared minus y squared over b squared equal to 1. All right. Next, we have the elliptic cone. 3. That already did 3. 4. We have the elliptic cone. Okay. So that's going to look like this. It's going to be a cone. Okay, so the cone opens up and down, and again, it's arbitrary which one of the axes it's going to open along. You can tell based on the equation. Okay, so for example, with the hyperboloid of one sheet, whichever of our variables is negative, so we'll have two positives and one negative variable. Whichever one of those has the negative inside is the axis that it's going to open along. So that's true for the hyperboloid of one sheet. For the hyperboloid of two sheets, we'll have two negatives and one positive, and the positive is the one that it's going to open along, right? So if you look back at those formulas, for the hyperboloid of one sheet, we had positive x squared, positive y squared, negative z squared. So that's going to open along z. For the hyperboloid of two sheets, we had positive z squared minus x squared minus y squared. So that also opened along z. Okay. With the elliptic cone, the formula is going to be x squared over a squared plus y squared over b squared minus z squared over c squared equal to 0. So if it's equal to 1, then we have got a hyperboloid of one sheet. If it's equal to 0, we have the elliptic cone. And again, you do not have to memorize all of this. You can have this written down on your 4x6 index card for the exam. All right. Okay, and you know which one of the axes this is going to open along, because in this case it's going to be the one that's negative, negative z squared. Number 5. Number 5 is the elliptic paraboloid. Okay, so that is going to be a parabola, but it's elliptic because it goes all the way around. Okay, so in this case, because it's opening along the z-axis, we have z is equal to x squared over a squared plus y squared over b squared. Okay, and 6, the last one, is the hyperbolic paraboloid. It is probably the most difficult to draw. It's also called a saddle. All right, it's given by the formula z equal to y squared over b squared minus x squared over a squared. And if this is the format that we have, it's going to look like this. Okay, so it's going to be parabola here. So this is in this first parabola that I've drawn here is in the in the y-z plane here. Then in the xz plane, we have another parabola opening down. Okay. Okay. So again, it is not an easy thing to draw this. It's actually quite challenging to draw it. So here I've got this parabola coming through the tops, and then here, like wherever I have these ending, I'll have another one coming through here like this. Okay, so it literally looks like a saddle. If you imagine the saddle, a saddle, like a horse saddle, that's what it's going to look like. So again, please see a picture of this online or in your book, as it is very difficult to draw this. So if I were to try to just kind of draw it just in kind of the dimensions you could see, it would probably look something like this. So it would come down and we would kind of have our saddle coming through here. There you go. Might kind of look like that. So this shaded region in the back would be kind of the inside, and this in the front is what we can see. But the strange thing about this is you have a parabola going up in one direction, and then turned 90 degrees, another parabola underneath it going down. Oh, that didn't help at all. All right, so let me just erase that. But that's kind of the idea. So if you just imagine a horse saddle, that's what we're dealing with here. Okay, so how do we sketch these? Well, to sketch them, we're going to sketch the traces. To sketch, we're going to sketch the traces in each coordinate plane. Okay, so that's the big idea of how we're going to sketch these. We need to classify it so we know what we're dealing with, and then we can find the traces and get them sketched. Okay, so let's do an example. So let's classify and sketch the surface given by 4x squared minus 3y squared plus 12z squared plus 12 equal to 0. Okay, so all of our quadric surfaces were equal to either 1 or 0. We do have a constant, so let's move that to the other side of the equation. And to get that to be a 1, we need to divide, so let's divide by negative 12. So this will become negative x squared over 3 plus y squared over 4 minus z squared over 1 equal to positive 1. All right. So it looks like we've got two negatives here, so let's rewrite that with the positive first. Y squared over 4 minus x squared over 3 minus z squared over 1 is equal to 1. And if we go back and look at the different forms of our quadric surfaces, this is taking on the form of a hyperbolic sheet. I'm sorry, a hyperboloid of two sheets. There it is. Goodness sakes. Okay, so this is going to be a hyperboloid of two sheets, and because the y squared is the positive term, this is going to open along the y-axis. Okay, so first of all, let me give the answer here for the classification. It's a hyperboloid of two sheets. Okay, and if I drew a rough sketch of it, we know it's going to open somewhere along the y-axis. So it's going to look something like this. So that's good news for us because we know right away that it does not have a trace in the xz plane. So there is no trace in the xz plane. So we're going to find the traces in the xy plane and in the yz plane. So trace in the xz and the yz and the xy planes. Okay, so for the yz, we're just going to set x equal to 0. For the xy, we're going to set z equal to 0. Okay. Okay, so for the first one, if I set x equal to 0, I get y squared over 4 minus z squared is equal to 1. So then we have, let's see here. This is a hyperbola, okay, and it's going to open along the y-axis. We already know that. So if I'm just going to draw just the yz plane here. So yz. This 4 tells me that we are going to be 2 away from center here, and then we are going to open in this direction. Now again, this is a sketch, guys. I'm not looking for anything insane. We just need to get an idea of what this thing is supposed to look like. So this is a rough sketch. So that's my trace in the YZ plane. So now let's find that trace in the XY plane. Okay, so there I'm going to set z equal to 0, so I get y squared over 4 minus x squared over 3 equal to 1. So again, we have a hyperbola, and I'm going to try to keep it like this. So here's my y, here's my z. I'm going to come out to here, to here, and it's going to kind of open along here. Okay, so if you need to refresh yourself on exactly how to draw a hyperbola, that's fine. You could also just put this into your graphing calculator if you needed to see it. But this is kind of a rough idea of what this is going to look like. So now we're going to put all that together. Come out two. So we've got this in the YZ plane, and then it's going to kind of come like this here. Okay, so we've got there. Okay, so there's our hyperboloid. That's just a rough sketch of it. We've kind of hit the highlights here of what we needed to see, and there we have it. All right, so I think we'll go ahead and end this section here. As always, if you do have questions, please let me know. I'll be happy to answer those, and highly, again, recommend looking up quadric surfaces online or in your textbook so that you can get a better idea of what those things look like.